Hi, welcome to the video lesson for Power Series, section 11.8 to 11.11. We'll be going in detail over the solution process for questions 1AB, 6AB, and 3A from the worksheet. A power series is just a different way to write an infinite series with the basic form of this over here, where C of n is the coefficient. Like in the previous sections, we want to test for divergence and convergence, but unlike the previous sections, we can use something called the radius of convergence. The radius of convergence can be defined as the positive number r where the function converges if the absolute value of x minus a is less than r and diverges when x minus a is greater than r. If we want to write all the values of x where the function converges, we write the interval of convergence. Let's go over question 1a from the worksheet. We've been given this function over here, and we want to find the radius of convergence and the interval of convergence. The easiest way to test for convergence is to use either the ratio test or the root test. Depending on the problem, it can be easier to use one method or the other, but I'm going to do both to show you how they work. Let's do the ratio test first. Using the ratio test, we get this set up right over here, and then when we further evaluate this limit, we get this over here. The reason why we set x plus 3 over 4 as less than 1 is because we're using the ratio test, and if the value is less than 1, then it converges. Here, we isolate our x minus a, in this case x plus 3, and so we get our radius as 4. Now, let's find the interval of convergence, and to do that, we need to isolate x. Because there's an absolute value sign, we get x equals 1 and negative 7, meaning that the function converges for all values between 1 and negative 7. But in order to figure out if 1 and negative 7 are included in the interval, we need to evaluate the series with 1 and negative 7 plugged in for x. Here, you can use the test for convergence we learned in the previous chapter. When we plug in x equals 1 to the original series over here, we get this, and then we can use the divergence test to see that as the limit as n goes to infinity of negative 1 to the power of n is not 0, it diverges by the divergence test. When we plug in x equals negative 7, because of the negative 7 over here, we also plug it into the original series, and we also see that as the limit as n goes to infinity is not 0, so we can say it diverges by the divergence test. Now, since both at x equals 1 and x equals negative 7, it diverges, we can say that the interval of convergence is from negative 7 to 1 with the parentheses. If, for instance, it had converged when x equals 1, we would have had to use a square bracket here instead. Here's a quick reminder. Only isolate x for the interval of convergence. For the radius, we only need to isolate x minus a. Now, let's find the radius and interval using the root test. Using the root test, you can see that we'll get the same thing as we did when we used the ratio test. So we'll get the same answers for the radius and for the interval of convergence. A good thing to remember is that the limit as n goes to the infinity of n to the nth root is always going to be 1, which is how we can just get rid of that. In this case, we could use both the ratio and the root tests. But let's say if you were given this function over here, you should use the ratio test because we don't know how to find the nth root of a factorial. Now let's look at another problem, question 1b on the worksheet. Find the radius and interval of convergence of this. Here's what we get when we set up this problem using the ratio test. As you can see over here, you have to keep the 2n plus 5 and multiply it by the 2n plus 3 because this keeps on multiplying on and on into infinity. And the 2n plus 5 is just the same thing as this over here. I canceled out the 2n plus 3 over here and the 5's over here. And then now we can simplify and get this over here. Now, when we do the limit, we see that it goes to 0. And since 0 is always less than 1, we can say that the radius is infinity. This means that we can say that the interval of convergence goes from negative infinity to infinity. Let's do one extra problem to see. Here we have this, and when we use the ratio test, we get this over here, and our limit ends up going to infinity. However, it doesn't always go to infinity. This means that our radius of convergence is 0. And when we find the interval of convergence, we can see that when x equals negative 2, the limit is actually 0. So we can write our interval of convergence as only 1 point when x is negative 2, using these squiggly little brackets. A power series can also be written as a Taylor series, where f of x equals this over here, where this little thing means to the nth derivative. Here are some Maclaurin series you should have memorized. We'll be using some of them in later problems. Now let's solve a problem, question 6a on the worksheet. Find the Taylor polynomial for e to the 2x, where n equals 3 and a equals 2. To begin, we first have to write a table. Here's our table with the 3 different columns of n, f to the nth derivative of x, and f to the nth derivative of a, which in this case is 2. Remember to always start at n equals 0. These values over here are our c of n from our form for the Taylor series, meaning that for our function, this is what our Taylor series looks like, and then you can expand it to look like this. Simplified even further, we can say that our Taylor polynomial is this over here. Let's go over question 6b. Find the maximum error for the previous approximation on the interval 1.8 is less than or equal to x is less than or equal to 2.2. For this problem, we have to find the remainder of the Taylor series, also known as the Lagrange remainder. Here's the basic form for the Lagrange remainder, where m is f to the n plus 1th derivative of x. For our problem, we can say that the remainder for n equals 3 is this over here. Here's our m, here's our n plus 1, which is 4, and our x minus 2 to the power of 4, because our n is 3. In order to find the maximum error, we need to find the maximum value for our m and for our x minus 2 to the power of 4. This means that we're going to plug in our x equals 1.8 and x equals 2.2 into each of these over here and over here in order to find the maximum. Let's start with m. To find m, we need to know the 4th derivative of e to the power of 2x, which we've added right up here. Now we can compare 16 times e to the power of 2 times 2.2 versus 16 times e to the power of 2 times 1.8. Since we know that e to the power of 2.2 is greater than e to the power of 1.8, we can say like this and say circle this, and we will use this value as our m. Now let's find the maximum value for our x minus a, or in this case, x minus 2 to the power of 4. When we plug in our x values for here, we get the same thing because 1.8 and 2.2 are both the same distance away from 2. We get 0.2 to the power of 4, which we can get this over here. Now we can plug in our m and our x minus a to the power of 4 values to get our remainder, which is 3.559 times 10 to the negative 10. Always remember this 4 factorial, or n plus 1 factorial, because sometimes we tend to forget it when we're looking for the maximums for these two. Let's move it up a notch. Evaluate the integral over here using series representation. This is going to be question 3a on the worksheet. To start, we have to rewrite the integral as a power series. Now we can rewrite 1 over x as x to the power of negative 1, and since we know what the power series notation is for cosine of x, which I've written right up here, we can rewrite the integral to this, which is just combining our 1 over x and our cosine of x. Now we can move the negative 1 from the x over here to the x to the 2n over here, since they're both to x, meaning that we can get x to the 2n minus 1 for our whole integral here. Now we need to find the antiderivative of the series over here, which can be found using this form, where the antiderivative of f of x, where f of x is a power series, is write this over here. Now we can apply that to our series over here, and we get this over here, where our c of n is -1 to the power of n, our x minus a to the power of n plus 1 is x to the 2n, because our a is 0, as we can see over here. And then we have our denominator, the n plus 1 times the original denominator, 2n factorial. Here are a couple of things to remember. First, when we use n plus 1 for finding the antiderivative, all you need to do is add 1. This means that if we have x to the 2n minus 1 in our power series, like we did over here, we get x to the 2n minus 1 plus 1, which just simplifies to x to the 2n, you see over here, and not x to the 2 times n plus 1 minus 1, which would get you a completely different exponent. Another reminder is that the n plus 1 you use on the denominator, so like the n plus 1 over here, is going to be the same as the n plus 1 you use in the numerator when finding the antiderivative. So this and this have to be the same, like you can see here where the 2n and the 2n. Also, if you have a denominator in the integral, like we did over here, be sure to keep it in the antiderivative. All right, that's the end of the video, and thanks for watching.